Primarily, I made a recording on your previous this topic alkenes, where I emphasized on Markovnikov's rule, electrophilic addition reaction, and all that. So now I'm not going to be emphasizing so much on those. However, I'm going to talk about the different kinds of reactions that alkenes do. I mean, practically speaking, reactions are something that everybody struggles to remember. So alkenes, reactions. If you memorize it every day, I mean, it's going to get easier every day. However, let's get started. So, the first reaction that I want you to remember is the very basic one, though. Whenever you have like an alkene here, let's say you have ethene here, this guy ethene will react with hydrogen in the presence of platinum catalyst, and it's going to form an alkane. So, this will be ethene to ethane. All right. The second reaction is with steam. If you decide to react any kind of alkene, let's say with steam, as in H2O, you must add here phosphoric acid, H3PO4, and you have to add heat. And you know that water splits into H plus and OH minus. Since I drew here like an symmetrical hydrocarbon, that's why OH and H, wherever it goes, doesn't really matter. But if I had here like an asymmetrical hydrocarbon, then of course you have to understand that the OH would choose to be with the carbon that has alkyl radical, and H would want to be with a carbon that is terminal, as in like that has more hydrogen to form a major product, and the reverse would be your minor product. So here, this is symmetrical. I don't have to really waste my energy thinking where will it go. So I can just put the hydrogen and hydroxide anywhere I want. So this is basically your alcohol. So you had like ethene and you created here ethanol. Great. Okay, now the next part is your hydrogen halides. Now, alkenes, since they're very reactive on their own due to the electron density region created by the sigma 1 and the pi 1 at the very middle, they don't need enough activation energy to react with halogens because halogens are practically very electronegative and they're diatomic, and whenever they're with a compound they can have electron differences, and as a result they can become polar, and as a result you can allow them to react with the chemical because polar chemicals are very loved by the double bonds. So they don't need any form of activation, so you can do this reaction in room temperature and pressure. So what's going to happen is this bond is going to open up. It's going to take in the H plus. Again, doesn't matter where because it's symmetrical. And then you're going to form here a halogen alkane. So from ethene, you have formed bromo ethane. Now, these are the basic three reactions for here. And what you can do is, and now we will talk about oxidation reaction. This oxidation reactions are where people face a lot of problem. All right, oxidation reactions are of two types. One is when you reacted with cold chemophore. Cold chemophore has to be dilute chemophore, and hot chemophore has to be concentrated one. A lot of people make a mistake and then they don't understand where the hot chemophore and the cold chemophore really works into. So remember that cold chemophore is dilute, whereas the hot chemophore is concentrated. All right. Now we are going to work with cold chemophore at this point. Cold KMNO4. KMNO4 is an oxidizing agent. This guy is an oxidizing agent. Since it's an oxidizing agent, whenever you're adding this, you don't have to write the entire chemical. You can just write oxygen with a square bracket to represent that you have an oxidizing agent in your reaction. And whenever it oxidizes a chemical, it changes the chemical's color from purple to colorless. Okay. Now, if I have a double bond anywhere, if I'm adding cold caminophore, and by the way, this caminophore, when it's cold, it is also acidified. So you have to mention that as well. So when I'm adding cold caminophore, I have to also add in my reactant side a little bit of water because this caminophore is not going to yield you the chemical reagent. This is an agent who's going to work for someone, and that someone cannot only be one element. I mean, think about it. If you add caminophore with cold, so you have to add water. So water is the guy who's going to provide H plus and OH minus. So when the caminophore is cold and you react it with some kind of alkene, it forms a diol. So what happens is it opens up the two double bond and forms OH. Wherever it's gonna have a double bond, and if you add cold caminophore, you're gonna end up getting two hydroxides, and we call it diol. It's called ethanediol. All right. But that's all about cold caminophore. There's nothing more to it. But when we add hot caminophore, the reaction is a little diverse, I would say, little diverse, because they don't behave in a certain way with other reagents. Hot caminophore is a little diverse. Now, hot concentrated KMNO4, and it's acidified as well. Now, when you have a double bond and when the caminophore is hot, they don't target more or less, they don't they don't kind of like target your hydrogen or double bond hydrogen or carbon itself. Now what it does is it kind of targets your double bond, and then first of all it breaks down a double bond and then it tries to burn up the chemical. If you have a double bond and you have on the both sides carbon with hydrogen being attached, no alkyl radical, this is simply going to break it apart and burn it down. When you burn any hydrocarbon down, what happens is it forms carbon dioxide gas and water. So what happens is if you have hydrogen attached to the carbon, and if you're adding hot caminophore, it's going to attack the double bond, it's going to burn the chemical down, and then form carbon dioxide, or it will oxidize to make it carbon dioxide. Now, what happens is when you have like an alkyl radical, when you have an alkyl radical here, and let's say two hydrogen here, first step, what happens is it breaks down the double bond. Okay, practically, let's break down the double bond. When you break down the double bond, it splits like this. As it splits like this, the double bond here gets oxidized. And this guy cannot get oxidized because it has hydrogen. So whenever it tries to get oxidized, when it has to be oxidized, it rather always forms, when carbon is attached to hydrogen, it always forms carbon dioxide and your water. But this side didn't just only have hydrogen, it also had alkyl radical. So this oxygen got attached to the double bond. And right now I have an aldehyde. What would you name this aldehyde? This aldehyde's name would be, how many carbons are here? 2. So it's called ethanol. All right. Ethanol is an intermediate compound. When you have excess of caminophore, if you are heating it under reflux, if you're not doing distillation right after you're heating it, you will further oxidize the aldehyde. You can oxidize a chemical as long as you have spare hydrogen with the central carbon atom. So you have a spare hydrogen here, right? So this is going to again oxidize itself and form here. Add here OH. So what you have formed here is an acid. So aldehydes, if you don't stop heat under reflux, and if you keep on heating it and doing reflux without distillation, you will eventually start creating acid, and that's called ethanoic acid because you had ethanol. If you had propanol, you would cause propanoic acid. That's like a common sense. Okay, so remember that if you want to stop in this stage, you can't do heat under reflux anymore. You have to do distillation. But if you want to go forward and further oxidize more, you have to come keep on continue and doing heat under reflux so that all the aldehyde that you had can be further oxidized to form a carboxylic acid. And the main reason why aldehyde can be further oxidized is because of this guy, hydrogen. The carbon needs to have a spare hydrogen. Now you must be saying, okay, so this carbon also has a hydrogen. Well, this carbon is not attached to double bond O. The carbon that is attached to double bond O needs to have a spare hydrogen. If that happens, only further oxidation is possible. Otherwise, it's not possible. Now let's look into another scenario, a more complicated scenario. What if you had a double bond? On one corner, you had an aldehyde, sorry, CH3 and H, and the other corner, you had CH3, C2H5. And you decided to add here your oxidizing agent, KMNO4, and it's hot, and it's acidified, it's concentrated, crazy. Now, it's going to break the double bond down. Let's break the double bond down. Double bond broken. The double bond is broken. One side CH3, the other side H, the other side CH3, the other side C2H5. The first thing it does is it adds it oxidizes it by adding in oxygen to the double bond. Now, can this be, if you're doing heat under reflux all over again, no distillation, what's going to happen is it's going to further oxidize. Since it has a spare hydrogen, it's going to further oxidize to form carboxylic acid right here. Does this guy have any extra hydrogen? Does this guy have any extra hydrogen to itself? No. So no further oxidation possible. So let's name this compound down. You had, you created here 1, 2, 3, 4 butanone. This is a ketone. And you had here ethanol that became your ethanoic acid. And how will you name this guy? Let's say this is 2. If I take this one to be the longest chain, for example, this is carbon number 1, 2, 3, 4, 5. So this is like pent2-ene, and this is like 3. So 3-methyl pent2-ene. Now, how did I get pent2-ene? Okay, let's see it like this. I had here like 2 carbon, right? So 1, 2, 3, 4, 5. From left to right, you had like 1, 2, 3, 4, 5. From right to left, 1, 2, 3, 4, 5. So where is the smallest number? 2 is the smallest number here. So pent2-ene. And in the third position, I have my methyl group. So 3-methyl pent2-ene. Okay, that's how I named it. Simple, not that hard. All right, so long story short, what did you guys understand here? I said that if you have like a double bond, and if one of the carbon in the double bond has like hydrogen on both sides, it's gonna get oxidized readily and form carbon dioxide and water. It's like combustion. However, if you like have a alkyl radical in one corner, it's gonna break apart in such a way that that part is gonna gain, the central carbon will gain oxygen, it's form an aldehyde. If you don't stop heat under reflux, if you keep on doing heat under reflux, you're going to end up oxidizing it further and making carboxylic acid. But if you decide to stop at aldehyde, you can do distillation and stop heat under reflux. If you have a chemical where you have alkyl radical on both corners and the other side of the carbon has one alkyl radical, the one that has 2 alkyl radical will form a ketone, and the one with 1 alkyl radical will form an aldehyde, and then again acid. That's all. These are the reactions that you need to know for alkenes. So if you want to make it easier, you can simply just draw a spider chart. That's what makes everything seem to be very much visual and helpful to many of you. So for example, carbon-carbon double bond is right here. Okay, I'm making it asymmetric. If I add here HBr, what would I get? If I add here HBr, I would get CH2H. This is my major product. Or I would have gotten here CH2Br. CH2, CH3. This would be my minor product due to Markovnikov's rule. And this reaction happens at RTP. We do know that if you want to add here bromine water, it's going to decolorize the bromine water. That's a test of alkenes. It's going to form CH2Br, CHBr, CH3. All right. If you decided to add here hydrogen, but with platinum, then you would get here an alkene. You would get here an alkane, a beautiful alkane. If you decided to add here phosphoric acid, PO4, with as a catalyst, and then you decide to like heat it up, then you would form an alcohol. Well, when you form here an alcohol, again, there will be a possibility of major and minor product because this is not unsymmetrical. So here the major product will again be this carbon will get the OH, the nucleophile. So this is how it will be, the major, and the reverse will be minor. This will be the minor one. All right, now, what if you had to react it with, let's say, for instance, case, sodium hydroxide, but in aqueous. When you add sodium hydroxide in aqueous, the hydroxide acts like a nucleophile in this case, and you will end up getting here hydroxide in one of the reactions. But the issue is it will not be able to react because we only have what? We only have hydroxide as a compound, but it will not react. If it was an halogen alkane, it would have reacted. So these are the reactions of, so far, the reactions of your alkenes, but there are two more, as I've taught you guys a little while ago. One was cold KMNO4. If you decide to put a cold KMNO4, you have to put a little bit of water with it so that you can get here a diol. So it's going to be CH2OH, CHOH, CH3. Okay. Now, if you decide to add here hot KMNO4, so if you decide to put, let's say, hot KMNO4, at that point, I'll have to break this bond down. When the bond breaks down, what do you guys see is happening here? You guys can now explain this. This part will get oxidized to form what? Carbon dioxide gas and water. However, this side has one alkyl radical, so this is going to form here what? It's going to form a aldehyde. Further oxidation of aldehyde creates what? It forms carboxylic acid. Okay, this is it. So my reaction started from here. This is all about alkene reaction. Reaction number one, you add bromine, it forms a dibromo, your propane. If you add hydrogen bromide, it can form major and a minor product. If you add, let's say, phosphoric acid, since it's symmetrical, it's going to form an alcohol. Again, major and minor is possible. And then if you add platinum with hydrogen, you're going to form an alkane generally. If you add here cold KMNO4, you're going to make diol. If you add hot KMNO4, you're going to make oxidation happen to be acid, ketone, aldehyde, carbon dioxide, and water. Okay? All right. That's all about alkenes and its reactions. Further will be analyzed when we learn about halogen alkanes. So today, I'll keep up till this much. Bye-bye, guys. I hope you liked my video.